Well, good afternoon, everybody. I'm just waiting for everybody to join. While that we're waiting, let me introduce myself. For those of you who don't know me, my name's Jeff Eggleston. I work for IBM. I work in the hardware division called Systems, and I'm chairing the event today. The event today is 1BD. Why am I telling you that? Because I'd like you to fill in the feedback at the end, which is what GSE thrives on, so that we can do future events based on the feedback. So please, at the end, can you actually do the feedback? As far as questions go, Steve's got a very tight schedule, but we have discussed that hopefully there'll be one or two questions and we will take them as they come. If they become quite a lot, then we might actually put it towards the end and allow the questions to be answered at the end. I'm just admitting a few more people. Just hang on, Right, I'm going to now hand it over to Steve, who's going to give us a Sysplex update. Steve, the floor's yours.
Thank you, Jeff. Good afternoon, everyone. I'd like to welcome you to ZOS Parallel Sysplex update. I wish I could be giving this in person, face to face, but we live in interesting times now, and I've always enjoyed presenting at the GSE UK, and have had the privilege of presenting for a number of years here, and so I'm very thankful for that. I would like to just welcome you here. Let me just tell you a little bit about myself. I work in what's called the IBM Garage for Systems. That used to be called the Worldwide Client Experience Center, and we help architect solutions with our clients, and particularly with leveraging some new technologies. And so I'm involved heavily with that. But the vast majority of my career has spent in ZOS development. So I have a very technical background. And we're looking forward to talking about a very loaded topic today, which is ZOS Parallel Sysplex update. So with that, let's move on. We have a lot of material to cover in a short time, so let's see how well we can do here. So today we're going to be talking about a number of different items. We're going to be talking about Sysplex recovery boost processing. And this is a new arm of system recovery boost that is applied specifically for recovery processes affecting parallel Sysplex. And so we're going to talk a lot about that. Some other presentations have sort of touched on that. We're going to go into a lot more detail about exactly how that boosting behavior actually takes place. We also are going to talk a little bit about some of the coupling facility enhancements that have been made in the latest Z15 for CF level 24. And so we're going to talk about that. And as time permits, if we get through those first two topics, we will talk a little bit about some ZOSMF Sysplex management enhancements and some Z15 hardware improvements and changes for parallel Sysplex. And then we'll have questions and answers at the end. So this is kind of what our agenda is, and hopefully we can get through all of it because there is a lot of material here. But that being said, if you do have a question and I say something that's not quite clear, by all means, feel free to ask as necessary. All right, so let's begin. Okay. So the first thing we're going to talk about is boosting Sysplex recovery processes. So you may have heard of something called System Recovery Boost, which is a really cool, probably the flagship feature of the Z15 hardware family. And this functionality has now been extended to support something called recovery process boosts. And Sysplex failure recovery processing takes advantage of that in many cases and helps to make that recovery processing hopefully less impactful to your shop on these rare events that take place. So we're going to be focusing a lot of our attention on that right now. So just as a quick overview of what System Recovery Boost is, System Recovery Boost really allows you to maximize your availability and try to reduce these outages or disruptions in your workloads substantially faster than on previous Z boxes, right? It's built into Z15. There's a base component of System Recovery Boost that is available to everyone at no additional charge. And the goal of it is to give you extra horsepower to deal with some of these service and recovery issues on your system without impacting your IBM software licensing costs. Okay, so you're given more horsepower, but you're not going to be charged for that extra horsepower during these things called boost periods. So just to give you a quick overview of System Recovery Boost, we have faster shutdown and startup of our LPARs during you can trigger a boost during a shutdown of your LPAR by invoking a proc. Then you can, once the shutdown has been given additional horsepower to complete quicker, GDPS can also have more rapid automation of its processes to, to perform its actions quicker. Then when we are actually restarting and IPLing the system, we can avail ourselves of this additional horsepower. And finally, when we get to all the software, the middleware, and our applications are up, we are given extra amount of boost period to actually be able to recover those workloads. And so this is a great thing of System Recovery Boost. Again, the backlog, the additional space can be used as work has been building up as you're rebooting the system. You have the ability now of being able to have this additional amount of time to help catch up and return back to normal operations using this boost period. So again, trying to have the mean time to recovery for an IPL to be faster. The latest thing available in September of this year was something to improve Sysplex recovery. So parallel Sysplex recovery processes now can also be boosted to return to a steady state operations much quicker. And so that's the focus we're going to be here. Phase one or stage one was to deal with IPL boosting, re-IPLing the system. And in stage two, we're dealing now with Sysplex recovery processes, also being able to avail of this system recovery boost. So let's talk for a moment here about the big Sysplex recovery processes. So Sysplex is a very resilient environment, but there are cases where we do have recovery processes that need to take place to handle certain types of failures. And these survivors of these particular types of failures sometimes have a significant amount of work that they need to accomplish to recover from that. And these failures include things like a disk failure, a failure of data sharing members with locks held. You have system failures within the Sysplex. You have a CF structure failure, as well as a couple of the other failures listed below. Now, the failure recovery processing that is to recover from those failure situations is usually a short duration, but while that failure recovery processing is going on, in many cases, that can be impactful to the existing workloads that are running. And we want to minimize the amount of processing the amount of the time window of which these recovery processes need to complete. And we want to be able to give more processing power potentially to your workloads so that that is less impactful to your system when you have to do these recovery actions. So this is the idea of the recovery processes that are taking place in the Sysplex. And so with these recovery process boosts, this new flavor of System Recovery Boost, we are boosting 4 types of actions. We have hyperswap, we have CF data sharing member recovery, we have Sysplex partitioning, and we have CF structure recovery. Each one of these actions can avail themselves of the Sysplex recovery process boosts. And the idea, again, is that we're going to be able to recover quickly the workloads and be able to resume normal operations as fast as possible. Now, there are some restrictions. Let's talk about the little ins and outs of recovery process boosts. Now, unlike the IPL recovery boost, which I can have 30 minutes of shutdown followed by 60 minutes of startup recovery boost for a total of 90 minutes for a boost, these recovery boosts are short bursts. And the reason being, for the most part, these actions generally don't take nearly as long as it is to take to shut down and IPL your system, right? So they're given up to 5 minutes of boost time to boost these recovery processes. And there's a maximum for an LPAR within a 24-hour period of how much I can be boosted for recovery boosts. And that limit is 30 minutes. So I have 30 minutes of recovery process boosts per day. And that's accumulated in a timer that's kept internally to ZOS. And the last item I'll mention is that both general purpose processor speed boosts and zip boosts can be leveraged for Sysplex recovery process boosts. And so now we're just going to have a quick refresh of what those two different types of boosts are. So in a pictorial diagram, we have general processors that usually on your system are running, are configured as subcapacity processors, meaning that there's additional horsepower that I'm not intentionally not leveraging to keep my software costs low, right? And so I have this subcapacity general purpose processors. Well, during a boost period, when the system is requesting a boost, those general purpose subcapacity engines can be dispatched as full capacity during that window, and yet from an SCRT perspective, they are not reported as such. And so they will be reported still as you're running as subcapacity, even though for this boost period, you are running at full capacity. So if you are running a subcapacity machine, which a vast majority of clients do run, you can avail yourself of speed boost to actually give you a larger share of that processor when in this boost period. The second type of boost is called a zip boost. And the zip boost, again, allows additional engines to have the distinction of being a blurred processing. So what do I mean by that? I can bring additional zips into my configuration that are reserved processors for that particular LPAR. And if I have backing of real zips to match those reserved numbers that I have defined in my image definitions, I can bring them online. And what's great about it is that not only do I have additional zips, but I can dispatch general purpose work on those additional zip engines. And so I'm having a blurring. So from the perspective of dispatching general purpose work, it can run either on a GP or on a zip during that boost period. Whereas normally, of course, GP work runs on GP processors, zip gets dispatched on zip. So in this case, there's a blurring, and I can use those zips for either zip work or for GP work. So again, having more parallelism, in addition to having larger engines in theory to run in, I have a parallelism aspect as well. Okay, so just a couple details about zip boosting for recovery processes. So just a couple of distinctions here. Normally, I can have for the IPL boost, I can have many, many different engines that I can bring in to have a huge amount of parallelism, up to 20 in the case of an IPL boost. For a recovery process boost, I am limited to a much smaller number. And that smaller number is going to be 2 transient zips, as they're called, which means that those zips are going to be blurred, and I can dispatch GP work on those additional zips that I bring in as part of the boost period. So I'm limited to 2. So when those 2 engines are going to be brought online, and when the boost period is done, those logical processors are also automatically be taken offline. Of course, when I'm in the boost period, I'm not subject to normal capping limits that I have for the image as well. And the last distinction I'm going to make on this slide is that there's this optional paid option called SRB upgrade, which I can avail myself of for IPL boosts. And this upgrade allows you to take dark engines, and it's very similar to the way capacity on demand COD works today, where I can temporarily upgrade the capacity of my machine using dark engines, for example, engines that are there on the machine physically, but they're not actually, you're not paying for those engines, they're not being utilized. I can temporarily bring those engines on in this SRB upgrade, the System Recovery Boost upgrade paid option. And I can avail myself of a lot more parallelism to dispatch general purpose processor work. For Sysplex recovery process boosts, the upgrade is not eligible. So we cannot use upgraded engines to facilitate this. Okay, so again, SRB upgrade does not apply to recovery process boosts. Okay, so now we're going to talk about the 4 exploiters of these recovery process boosts. And the first one is hyperswap. So just as a refresher about what hyperswap is all about, I mean, hyperswap is a coordinated Sysplex-wide recovery process that's going to restore access to DASD devices following the failure of some way. So in other words, you have some sort of a disk failure, most likely. It could be a planned failover as well. But most likely you have a disk failure and you want to switch over to what's referred to as the secondary disk, right? So you have a primary and a secondary disk. Hyperswap manages making these copies, and during a hyperswap processing, I'm going to actually move my primary disk over to a new disk for availability considerations, right? So when this hyperswap processing is being done, each system is going to need to do some amount of work, right? Sometimes we see a particularly slow processing system hanging up a hyperswap. So you might have a bunch of fast systems, you might have one slow system. And since all of them sometimes have to participate in recovery, we want to make sure that even that slow running system is going to have the capacity it needs to perform its hyperswap processing faster, so it doesn't hold up the faster utilizers of hyperswap. So let's go to a simple example. I just picked GDPS as an example of a hyperswap user, and imagining some sort of a disk failure here. So imagine we have these systems in a Sysplex here, and we have a primary disk here in the middle, and the middle is being X'd out here. In other words, I have some sort of a failure on that first disk. So when hyperswap is complete, I'm going to now move over to the next diagram, and the subtle difference is that the red lines have changed here. We're trying to move over to this right DASD here. The idea with when hyperswap is complete, that all the systems are pointing to the new primary, right? So again, the idea is that sometimes we might have some system, maybe it's the system on the right, for example, it's really not keeping up. So the idea behind the system recovery boost here is to give a little more horsepower so that he can keep up. So often in a Sysplex, we might have a low weighted LPAR, right? There might be good reasons for that. Maybe we have a test system in our production Sysplex, and we don't want to give too much CPU resources, and so therefore we give it a low processor weight. And that's great in terms of making sure that the production systems have all the resources. But what happens when you have a Sysplex-wide process running, such as hyperswap recovery? Well, when you have this hyperswap recovery, that can really hurt you by having that low weight. These other two systems shown on the left, for example, might be your production systems, and they're hung up waiting for that low-weighted LPAR to complete its processing. Now, of course, we know that even if you have a system recovery boost, that you can't exceed your weight of your LPAR, right? If those other systems are fully busy and you may not, you're only going to get the weight of your LPAR. But when I bring in the additional capacity onto the KEC and during a boost period, I'm still going to get the percentage that I have for the weight of that entire machine, I'm going to get the boosting for that particular that percentage that as proportional to the weight that I have on my system, right? And of course, if those other two systems on the left are not fully utilized, I can now, of course, exceed beyond my weight to be able to have this additional capacity. So adding the additional capacity is not a one-to-one corresponds. I add 2 extra zip engines. I'm not going to get full use of those 2 zip engines by the system that's slow, for example, but I am going to get my proportional weight of those additional engines, right? So and in terms especially for the speed boost, right? So the idea is I want to give the systems more horsepower to complete their operations, right? And so this is the idea of a hyperswap boost, right? So, all right, now let's talk a little bit more about the second kind of boost, which is a failure of data share members with locks held, okay? So if we're looking at a data sharing member, right? We have this, we're thinking about a lock structure connector, right? So on the right here, we have some systems. So in this case, we have 2 systems over here, and we have a system down in the bottom as well. And these are representing the systems in our Sysplex. And we have a lock structure here that's represented by this vertical bar here. And in this case, we have a cache structure, which maybe represents the data that's serialized by the lock structure. Of course, your data sharing application doesn't have to have a cache structure, and the lock structure could be used for something else to serialize, other things. The bottom line is I have data that needs to be serialized, and I have a lock structure that I'm using to accomplish that, right? So the issue we have is that if a connector listed at the bottom here, so if you look down at the bottom of the screen here, we have a connector that fails. Okay, so in this case, let's say maybe the address space just fails. That I have a connection to the lock structure, and the address space that has that connection suddenly just goes away. The surviving connectors can't access that data because their locks that are still being held, right? It looks like it's still serialized. So what are we going to do? So in this case, we have to go through recovery processing to let all of those connectors recover from those locks and thereby get access to their data, right? So from the time they can't access to their data, your application is really held up, right? Because it can't get access to the data that it wants. So this recovery can be pretty extensive, right? The connector may have been holding tens of thousands of locks, right? And we need to go and do recovery for all of them, right? So the idea is that I need to resolve, the survivors need to resolve the lock intention. It may need to release and take over locks, and it might need to back out or complete the in-flight transactions, right? So again, we want this recovery to go as fast as possible to be able to boost. And so we want to be able to boost these surviving systems that are also connectors to the lock structure so that they can perform the necessary cleanup, that they can perform their work. So if the locks are held when a lock connector goes down, so let's talk a little bit about the scenarios when this comes into play. So for example, if a connector disconnects with locks held, the notification says XCS is going to be sending notifications to all the other connectors, and those other connectors are going to have to perform this recovery processing. So if he explicitly disconnected, if that particular connector just goes away through task or address space level termination, the same thing. says it's going to detect that. It's going to send notifications to the other connectors to that structure, to that lock structure. And lastly, if the connector system completely goes down, it's going to be assumed that that guy may have held locks of the guy that went down. And so we're going to need to, again, be driven for recovery processing in that example as well. So again, we're going to have one boost for every per failed connector. So the recovery processing for each one of the failed connectors would be asking for a boost in this case, right? And so again, this is the mentality of when the actual boosts are going to be requested. All right, the third type of boosting that we were talking about in these recovery process boosts has to deal with a system termination in the Sysplex. So imagine I have a bunch of systems in the Sysplex and one guy just suddenly goes down. God forbid, once in a while that may happen. You get a disabled wait, or you have some kind of an outage, or it could even be a planned outage, right? Or you have you're bringing it down explicitly, right? So regardless, the surviving systems are going to need to do Sysplex recovery actions, right? And we know that process is pretty involved. So here just gives a list of some of the things that need to take place when you do a Sysplex recovery. The first thing is you're going to have a race condition to determine who is going to gain ownership of this particular Sysplex partitioning. So first you have to detect that the guy is no longer there. There's a race to see who is going to win. Whoever does that is going to update the Sysplex record. They're going to say the system is being removed. They're going to signal all the other systems in the Sysplex who are going to notify the local members that that's going down. There's going to be some isolation of that particular L part. And again, trying to isolate and get that guy out of the Sysplex as quickly as possible to avoid sympathy sickness for all the other systems in the Sysplex and to avoid work being sent to that system, right? Again, updating the couple data set again to indicate the system is no longer active. And now here's where all the cleanup is going to take place for the particular Sysplex. And there's a lot of cleanup that's going to be taking place. Eventually, a Sysplex record is going to be updated again to release the ownership claim and a message IXC 105I. The system has been removed from the Sysplex. But even when that message is issued, there still could be underlying asynchronous recovery processes that are still running on all of these other systems. So there's a lot of cleanup work. There's a lot of things that take place to partition a system out of the Sysplex when you have an outage. So what have we done for mean time to recovery for Sysplex for system failures in a Sysplex? Well, there's been a lot of things that have been done in recent years. And a number of years ago, there was a concept in XCF known as system status detect, which by using BCPII, the Sysplex is able to quickly detect a demise system. And of course, you want to be exploiting that technology. If you don't exploit that technology now, you want to exploit system status detect. It's a really game changer in terms of auto detection of a demise system within the Sysplex. And again, so again, to deal with a system failure, you have to first detect that you have a failure to begin with. Secondly, you're going to have to run through the Sysplex partitioning process as fast as you possibly can. And then you're going to want to run through the cleanup as quickly as you can, again, to restore normal operations with the remaining systems in the Sysplex. So again, BCPII and SSD is critical for the partition because you can't proceed with partitioning until that system has been isolated. And sometimes the BCPII way is the only way to reliably perform this isolation without operator intervention. And so we want to use this fencing as much as possible so that we can then clean up that removal of that system from the Sysplex and resume our surviving systems to pick up the workload as much as possible, right? So here's a picture diagram to describe what we just talked about here. So we have a two-system Sysplex here, and in this example, system 1 goes down. Okay, so in the Sysplex goes down. So the idea is, of course, we want to get that failed system started as quickly as possible to restore the full capacity of the Sysplex environment and possibly, of course, eliminate, in this case, a single point of failure, because now I only have one system left in the Sysplex, right? So first of all, there are technologies that are already in play to help this process move along. So, we have auto IPL that can help facilitate restarting the system quicker. We have GDPS that can come into play here. We have the concept of auto reply, which is a ParmLive member that you can configure to avoid operator intervention, to auto respond to certain messages, etc. So those things are already in play, but now we can leverage the IPL version of System Recovery Boost, the 30-minute shutdown and the 60-minute boost for startup on the failed system. So the failed system can take advantage of the System Recovery Boost to provide that system's on a Z15, of course, and it can leverage both that speed boost and the zip boost, and even the System Recovery Boost upgrade if you've purchased it and activated the System Recovery Boost upgrade on that KEC. Now, what about the surviving systems, though? So the surviving systems that are partitioning that guy out of the Sysplex, this is where, again, the Sysplex recovery boost for termination comes in, right? So even if you have a very well-structured Sysplex designed environment, you have work cloned on all the other systems, you're able to process the work through the use of shared queues from the coupling facility, and in effect, you can mask that there's a failure on the system. There are still issues where you need CPU cycles that are taken away from your applications for this recovery process, and we just talked about before. So the recovery process boost is going to help those actions as well by either giving your workload additional processing power and or giving those Sysplex recovery boosts additional horsepower as well. Now, from a capacity concern, all the surviving systems, of course, are going to get this recovery process boost when the system is removed from the Sysplex. But remember, recovery boosts are very short-lived. They're only 5 minutes or less. And so you're going to be recovering. You're going to make those Sysplex recovery actions faster. And of course, if you've already exhausted your 30 minutes for the day, you might not even be getting any boost in this period. So this is saying that you still need to do your capacity planning when you have determined to plan for the idea that you could have an outage on one of the systems on the Sysplex. So if I have 3 systems in my Sysplex and I lose one, I now only have 2/3 of the processing power I had before. And so what am I going to do so that I can still meet my SLAs, or that I can, live with that? So, I mean, whether you're using on-off capacity on demand to give a little more horsepower to those failed systems, to the non-failed systems, while the other system is coming back up, so I continue to make my workload and I don't have too much queuing going on. Whether you manipulate the workload in some way, the bottom line is that capacity planning is still required here. This boost is not going to be enough to be able to offset the fact that you lost the system, right? So you're going to still need to do the same capacity planning concerns. The recovery boost here is going to facilitate a quicker cleanup and partition of that guy out of the Sysplex, and going to minimize the disruption to the workloads that are currently running, of course, as well. Okay, the last boost that we have for the Sysplex recovery process boost is for CF structure rebuild. So just as a refresher, what CF structure rebuild is, it's the process where, again, the Sysplex is going to allocate a new instance of a structure, populate that structure with data, and then proceed to use that new structure instance, okay? So this process really is the foundation for failure, for all CF structure type of failure things. And even if you have duplexing, to populate a duplex structure, you're going to have to do a rebuild in order to duplex that structure. So even for duplexing, rebuild does come into play. The issue with rebuild is that you need to go in through these various quiesce phases in which you stop all the activity on that structure. So you can imagine that this structure is quiesced, and that basically no reads or writes are allowed to go to that structure. Why? says on XES on ZOS can do a point in time copy of the data in the structure, right? And so I need to make sure that that is totally quiesced. Well, when that quiescing is taking place, what's happening? Applications that need access to that structure, they're not running. So we want the rebuild to be as fast as possible to minimize this disruption, because while that rebuild is taking place, that structure can't be used. And so we want to get that rebuild to be completed so that employers can resume the usage of that structure quicker. So again, what we already have mean time to recovery improvements in the areas of structure rebuild, right? So we have message-based event processing that's been around for a while. This is going to allow you to use event processing instead of policy event processing. And this is going to reduce contention on the CFRM coupled data set. This is a good thing. We have serial rebuild, which has been around for many releases, I think all the way back to 2.1. And instead of just rebuilding everything at once, instead, with serial rebuild, we rebuild things in batches with the most critical structures going first. For example, GRS lock structures, which are sometimes other rebuilds are dependent on. And so we have a smart technology about how we rebuild the structure. And again, with duplex structures, again, the fastest way to accomplish a failover, but even then, we still need to suffer a rebuild to initially get it into that duplex state. So rebuild is still in play again for that. We have MTTR improvements for this, but there are still delays during this quiesce period. So when are we going to actually leverage a boost? So the key to know when a structure rebuild is going to leverage a Sysplex recovery process boost is when there is a failure of some sort. So again, when the structure rebuild and duplexing failover is taking place, and it was triggered by one of these events, this is very important to understand. Not all structure rebuilds will get a process boost. When you're triggered by a CF structure failure, a CF failure in general, or a loss of connectivity to the CF, that is eligible for a Sysplex recovery process boost. Okay. If you are doing a planned reconfiguration, so if you're issuing a set XCF start, reallocate, a rebuild, or rebuild duplex, that is not eligible for a boost in this case. So that's a plan and an action that you're taking on your own. But when we detect that a rebuild or duplexing failover is being triggered by one of those failures, we will actually then boost the systems. And again, the participating systems are including those that have a connector to the recovering structure. And if you're doing message-based processing, the system that's doing the event management will also request a boost. So now let's just talk a little bit. We've talked about the 4 types of actions in Sysplex recovery that get boosts. So now let's just quickly talk about triggering events that may spawn these multiple requests. So for a system termination, a surviving system will request a boost for each terminated system and each lock structure connector residing on the terminated system. And for loss of connectivity, again, each connector for that particular structure will request a recovery boost, etc. So again, each system independently is going to understand when is participating in an applicable recovery process boost. So potentially it could be all the system subset of systems in the Sysplex or all the systems in the Sysplex. But it doesn't have to be all of them. It depends on timing and other factors. And again, it's not necessarily synchronized. It could be recognized at different times. Each system acts independently to request the boost. Now, there is, as part of this new stage 2 recovery boost processing, a general command which applies both to IPL boosts and recovery process boosts. And a lot of folks have said to me, when I can't really easily tell that I'm being boosted, I have to go out to the HMC in order to find out that this LPAR is being boosted. and look at their displays, I want a ZOS command to let me know that I'm being boosted. And so if you do a new DIPL info boost state command, it will now show both IPL boosts and which boosts are activated. And in the case of a recovery process boost, even the requester or requesters that are actually making the boost. So in this case, we see that the maximum of two zips have been brought online as part of the zip boost for the hyperswap activity that's going on in the system. There's also a DM equals CPU can also show which CPUs are now being boosted for zip boosts as well. So there's a couple commands that are there. So let's talk a little bit about recovery boosts versus shutdown IPL boosts. So if you are in the middle of a shutdown IPL boost, you will not be able to do a recovery process boost. And that is probably a good thing. And we'll also say that if you are in a recovery boost and all of a sudden there is a shutdown boost is initiated during that, you also are going to cancel that recovery process boost. In both of those cases, that's good news, because shutdown IPL boosts are much larger than these more targeted Sysplex recovery boosts. So they last a lot longer. There's a lot more capacity that can be brought online, and I can even use the upgrade boost for Sysplex for IPL boosts. And so again, you can bring additional transient zips in beyond the max of 2 in an IPL boost. And the last reason why it's good is because your LPAR, which has a maximum of 30 minutes per day of Sysplex recovery process boosts, that timer will be turned off when that occurs, and you will not incur those minutes. So you'll have more minutes for, God forbid, you have to do a Sysplex recovery action within the next 24 hours. So again, this is the relationship between shutdown IPL boosts and Sysplex recovery process boosts. So a lot of folks now are going to ask the question, what is the effectiveness of recovery process boosts? And of course, you know IBM, whenever you give a loaded question like that, what do we always say? Your mileage may vary. It depends, right? And it's really true, though, because there's a lot of factors that go into how much of a difference the recovery process boost is going to make. There's a timing issues. What's the distribution of triggers for the recovery processing? The load, how much recovery processing is there actually to do? If I have a lot of recovery processing to do for a particular action, if I have tons of connectors that I need to resolve, for example, I might see a greater impact of the recovery boost because I'm doing more work. If I have very little work to do and I give it a boost, yeah, I'm going to boost a very small activity. So that little activity is going to run a little faster, but it's not going to make a big difference. If I have a lot of activity to run and I'm boosting it, I'm going to see bigger effects. And of course, competition. Who gets the engine? Who gets the resources, right? So recovery processing is not a guaranteed access to additional resource that's brought online as part of a boost. So again, we have additional capacity that can be consumed by other work. So again, that additional capacity may not be needed again as well. So the bottom line is that the boost is going to make the recovery processing less impactful, whether it minimizes the duration of the recovery processes that are running on, or it helps maintain the workload capacity by offsetting the cycles consumed by the recovery processing. So if your workload suddenly now is with the recovery boost, instead it's very high priority at equal priority to Sysplex processes, well, that workload is now getting more engines to run. So now, even though you're running this other workload, meaning Sysplex recovery, my existing workload is now has more resources to it as well. So whether it's boosting that or whether it's boosting your workload, you're still going to get some benefits with having the recovery process boosting. What do I need to enable Sysplex recovery boost? Well, I need a Z15, whether it's the first T01 or the single frame T02. I'm going to need one of those. I'm going to need to upgrade my firmware to this level, and I'm going to need to have PTFs either on 2.4 or 2.3. So this is going to work on both releases. And This next slide talks about the umbrella APAR, which if you apply this APAR, it will prereq all these other LPARs. And of course, excuse me. And of course, what IBM recommends when you're installing things is to use fixed cats. And so if you use the fixed cat IBM function system recovery boost, you will automatically get all of these fixes to enable both flavors of system recovery boost, whether it's IPL boost or it's Sysplex recovery process boosts. Okay, let's talk about CF level enhancements. I told you that would be the vast majority of our presentation would be about the Sysplex recovery. Let's talk about some CF level enhancements. So I'm just going to dive right in. There's something called Fair Latch Manager that was introduced in CF level 24. So prior to CF level 24, we had the idea that all these CF tasks that could potentially wait for latches on this global suspend queue. And because you had this one big queue of which everything had to go through, there was a greater chance to have contention issues and cache line misses. And so the efficiency and scalability to CF was compromised in some cases. And to make matters worse, the dispatching and latching algorithms could result in latch fairness issues. What do we mean by that? It means that there was a non-deterministic way of which task would receive the latch next. And so it meant that sometimes newer requests coming in could sometimes cut in front of other requests that had already been waiting. It wasn't a FIFO type of queuing mechanism. And so you had some requesters that might wait an inordinate amount of time because someone cut in line unfairly. And so with the CF level 24, again, there's nothing you have to do from an external point to exploit this function. The bottom line is they use this global suspend queue much less and as a result, it's much less a source of global contention, and you'd have less cache misses for the CPU and the CF. And then also you're going to have things are going to truly be FIFO. There's no more cutters in line, and you're going to have more fair latching. And again, the CF is more efficient at managing its work. The next one is message path resiliency. Now, a lot of these things are rare events on the system, and this is a rare event. So we have to describe how the system behaves before we can just determine what the problem is. And let's just talk about how the CF and ZOS communicate when ZOS comes up. So the CF message paths that we have between ZOS and the coupling facility use this thing called a ZOS provided system identifier, SYID, to uniquely identify the system image and the instance of that image. And so it's important for both ZOS to know what CF images it's talking to, and it's important for the coupling facility to also understand what ZOS it's talking to, particularly for when you're dealing with such things as Sysplex cross invalidates. So when a ZOS system IPLs, the message paths are already supposed to be deactivated when you did a system reset, and their system identifiers are supposed to be cleared during that process. But on rare occasions, that doesn't get done. And so from a CS perspective, an incorrect system identifier persists, and it prevents delivery of the messages on that particular message path. So on these rare failures, a system reset does not always clear this. And so with the Z15, the bottom line is that there's additional information that's provided to ZOS. ZOS, when it comes up, is going to make sure that everything is correct. And if it's not correct, it's going to take a non-disruptive dump on the CF about why this thing wasn't cleared out. And it's then going to reactivate the paths. So no matter what, you're going to always have all your paths between the coupling facility and ZOS activated and restored. Again, nothing you have to do to enhance it, just a resiliency, availability improvement with a coupling facility. Now, here's a function that's been around for a long time, and this is called dynamic dispatching equals thin. This has been around since the ZEC12. And the idea is that coupling facility images can run, of course, with either shared or dedicated processors. Of course, if you're with dedicated processors, you're going to have the best performance for production CFs. That processor's sole responsibility is to process incoming work coming off of from the link hardware coming to coming to the coupling facility. However, many times for test development and even some production CF environments, we may use the idea of shared processors because it's more economical to do so. So if I have shared processors for my coupling facility, there are several different dynamic dispatching models that are already out there. So the default prior to the ZEC12, there's only one way, and that was Prism and LPAR time sharing. So basically, when you have a time slice and that Prism has determined that you have a time slice, it will give your coupling facility control. Your coupling facility code will then go out to and see if there's something has arrived on the link buffers, and then process that request and then relinquish control back to the Prism for it to give its shared resources to maybe another LPAR. Dynamic dispatching equals on was an optimization over that, which basically you still receive control the same way, but rather than just relinquishing the control immediately back to Prism after I've processed those things in the link buffers, I'm going to just hang around for a little bit and see if there's additional work that needs to be processed before I just go ahead and relinquish control. Once there's no more control, or once Prism yanks it away from me, I now don't have control anymore. So this is the dynamic dispatching equals on. In the ZEC12 timeframe, they went to an interrupt-driven model as an alternative dispatching model for the shared engines. And so this is a way for the link hardware to now generate an interrupt when something arrives in the link buffer. That interrupt is going to cause Prism to say, oh, I need to give control to this CF because there's work to do. So this, of course, is a logical way to do things. You drive it with interrupt, the CF will receive control, it will process the work, and will then relinquish control, waiting for the next time that an interrupt comes in and Prism receives control again. Because this has been proven to be a very effective way and well-performing in many environments, this is now the default behavior when I'm running shared processors. And so on the Z15, the default has been changed now to using thin interrupts as the default action. And now the big one that was just introduced in GA 1.5 is called this idea of CF monopolization avoidance. The idea is that a coupling facility has a finite number of tasks which do its processing. And in some rare cases, there could be a case where a single structure consumes such a disproportionate amount of those tasks, it starves out and basically squeezes out other well-behaved structures on the system, and those guys cannot get control, or they get control in such a delayed fashion that their performance is greatly impacted. And so again, workload throughput is badly degraded across the Sysplex. Now, the good news is that this is really hard to create and it's rare. But when it does happen, it's really, really, really painful, and it's not something that you want to do. So to have happen. So the solution is that the coupling facility and ZOS are going to jointly cooperate to try to avoid this monopolization of a particular structure. So the coupling facility's role in this is to be the notifier. So the coupling facility is going to go out there, and it's going to, when it detects that a particular structure is monopolizing almost all the tasks and preventing other tasks from running in a timely fashion, other structure work to run in a timely fashion, it will send back a response to ZOS that the structure that this request is for is monopolizing the structure, is monopolizing, the tasks on the CF. ZOS is then going to take some action. It's going to then monitor the situation for a while and see if that problem persists. And if that problem persists, it can throttle back the usage of that structure to allow other structures access to the tasks that are in the CF and allow them to work. So again, workloads that would formerly have been victimized by an abusive workload are going to now run to near normal service times and throughput. So there's some big concerns here. How do I determine that a workload just has lots and lots of requests versus a workload that has lots and lots of requests that's hurting other structures. And so this is one of the goals of this CF monopolization avoidance. There are lots of applications that have a high rates of structure activity. And of course, you don't want to be hurting those existing workloads. So of course, in the case of, for some folks that are nervous about turning this on, we provide what we refer to as a good old chicken switch, right? So you can just choose to disable the CF monopolization avoidance on ZOS, and so that we will not actually take these actions. But we highly recommend that you consider using it. All our initial tests and validation from our clients have shown that this works very, very well, and it does it in a very automated fashion. So this is the pictorial diagram of this. Basically, I have a structure. I have a bunch of connectors. I have a structure represented by the white arrow at the top that is not being monitored. It's not being managed. It's sending virtually an infinite number of requests to the coupling facility. If the coupling facility gives back an indication to ZOS that, yes, this guy's totally monopolizing most of the tasks, as represented by those yellow tasks inside of the CF, if this CF monopolization avoidance is activated, what's going to happen is now XCF is going to move to a monitored phase. And in the monitored phase, we're going to continue to look and see if this monopolization continues. If it does, we will then go to a fixed number of connections, n number of connections. And of course, that n number is going to be calculated about how many connections that it will allow to be run concurrently. Once you exceed that number of concurrent, once you exceed that number of concurrent things, the rest of them will be queued, right? If the problem still persists, it can go down to 2/3 of n and even 1/3 of n until the problem is alleviated. And then gradually it can go reversed and eventually not even be monitored and managed. So again, this is the idea of monopolization avoidance. And so there's a bunch of new messages that appear on the screen that says that monopolization management is now in effect. It's not monitored anymore, and how many requests are delayed and how many requests are currently delayed. So lots of information on the screen. So observations from our testing are that this is that when we have a monopolization, that synchronous service times are increasing dramatically, but when we have this CF monopolization avoidance, we actually requests for non-monopolized structures have reasonable throughput and service times. And in fact, even the monopolizing throttled structures get a benefit for a lot of our use cases. Even throttling it back can sometimes result in better service times, because now we have less latch contention, cache coherency, and long queues are sometimes avoided on the coupling facility. And so that's a weird side effect, that even throttling it sometimes can have a better throughput for that structure. So I'm going to skip over this slide and go right to the chicken switch. So the chicken switch can be enabled. Again, by default, it's disabled. This is a continuous delivery item. And if you know anything about continuous delivery items delivered to the service stream, we try to have absolutely minimal impact to a client, that we can provide new function, but we have a switch that will enable that function such that they apply the maintenance, they won't get changed behavior unless they explicitly ask for it. So we would highly suggest that you enable this function. And the way you enable it is either dynamically through the set XCF functions command, or of course, to make it a permanent change in IPL, you're going to update your couple-XX function statement to add this chicken switch CF monop avoid, okay? And again, this is not going to have a lot of benefit unless you do it Sysplex wide. So you can imagine I have two connectors to a structure. They're not going to take the full benefits, benefits of this, because you could have scenarios where I have a low request rate guy has the avoidance, and even though he detects that there's a monopolization of the structure, because he writes so few requests, even if he throttles it all the way down to the most restrictive phase, the overall amount of requests could still not be throttled, because the guy who's the big high request rate guy, he's not throttling. And so as a result, it really is an all or nothing thing. You want to enable this on all your systems in the Sysplex, all the guys that write to that particular, are writing to that CF. And here's the requirements that you're going to need. I'll just quickly talk about, we're at the top of the hour now. I'm just going to quickly talk about two functions in like about 5 minutes. We're going to go just a couple minutes over. So ZOSMF is a great functionality for a lot of early tenure folks, as well as folks that want a less error-prone mechanism for doing all kinds of management of ZOS. And the Parallel Sysplex plugin that has been available since 2.2 is just one of those things that you can specify in your IZU PARM to enable the Sysplex management plugin. And so once you have that, I have lots of capabilities. I can view Sysplex information. I can modify Sysplex information. So I can do all kinds of things like structure rebuilds, duplexing structures, couple data set creation, addition, switching, and a bunch of CF actions as well. And so, for example, for if I'm doing a modification, modifying structures and doing a rebuild, I can actually initiate this through ZOSMF. And which is really great about this, I love this feature that I can actually preview the commands that are going to be issued by ZOSMF on your behalf. And so the first time I do it, I'm not trusting ZOSMF. I want to see what it's going to be issuing. I look at the command and say, okay, yep, that's exactly what I would do if I wanted to do this action. And so I'm going to let it go. And eventually you can say, I don't need to preview the commands, and it will just do it. It also has a command log that survives IPLs that will allow you to gain more information about the rebuilds. And of course, it shows you the command outputs in a consolidated screen just for that particular action. So really cool stuff. There's also new enhancements for ZOSMF Sysplex management that have come out relatively recently that allow you to never have to write JCL for creating a couple data set ever again. There used to be some edge cases where, for example, if you were switching between an alternate to a primary data set, and now I wanted to allocate a new alternate data set, that I had to specify an existing data set when really I might want to be creating a new one. So I might have a primary and an alternate. I want to switch the alternate to now be the new primary, and I want a brand new alternate. You can do that now by now saying the format a new data set option listed right here. You can also retrieve those values with either the values of the current alternate CDS or by default values. It allows you to override those values. A lot of function here in the Sysplex management plugin, and they keep adding more and more function. It's really a cool tool. And if you see the visualization of the pictorial diagram of your Sysplex and be able to drill down and be able to do this functionality, very cool. Of course, it assumes that you give your ZOSMF user enough authority to be able to do these particular actions. And last but not least, I'm just going to talk quickly. If you just acquired a new Z15, some constraint relief, and just some considerations. So again, with the new Z15, the number of coupling chipids has increased from 256 for the prior generations of hardware to 384. And the ICA short-range coupling links went up a little bit, went up 16 more from 80 to 96 for that. In terms of participation in Sysplex, we know business as usual. When you get a Z15, we only support N-2 levels of hardware that can be in the same parallel Sysplex. And so this picture is worth 1,000 words. Right now I have an EC12 along with my Z13s and Z14s, and I purchased a Z15, either a T01 or a T02. I'm going to have to remove the Z EC12 out of that Sysplex. If I want to bring that Z15 into the Sysplex, I cannot have N-3 layers of hardware that's just not supported. And again, we've been telling for many, many years that the Z14 is the last model, the mother machine, not the ZR1, is the last machine to support InfiniBand coupling links. And true to our word, the Z15 does not support InfiniBand. And so your choices for short range are the ICA adapter, and for long range, the coupling express long reach. So again, you can creatively still use InfiniBand links if you as long as you're connecting Z13s to other Z13s or Z13s to Z14s, and Z14 not being the ZR1. The ZR1 only supports the same things as what the Z15 supports, which is just those ICA SR and the CE LRs. But if I arrange my Sysplex in such a way where the links between 13 and 14 can still use the InfiniBands. So I still have that capability, but I cannot use InfiniBands on the Z15. Okay. And here's the microcode levels that you need on the lower level machines when you're bringing the Z15 into the mix in your Sysplex. That's an awful lot of information. I feel like I talk like a motor mouth. And to be honest with you, most of these features are only introduced in the last number of years. There's almost zero material that I repeated from when I gave this session last year when the ZOS 2.4 came out. So there's a lot more features that I did not talk about. If you have other features related to ZOS 2.4 that you'd like to discuss, please drop me a line. My email is on the front page, and I'm happy to talk about any of those things like transport class simplification, single system logger couple data sets, and a whole lot more features that I could not cover in this time. So this is motor mouth presentation at its best. But I thank you guys for listening and staying with me for the session.
Steve, thank you very much. I see it's brightened up in your room because there's light coming through your curtain now. When you started, it was all dark. I really appreciate you getting up early hours of dawn to have this presentation. It's been phenomenal. I have actually picked up a few things. I also would like to extend thanks to people in the audience who have crawled out of bed early to listen to you, because I know it's quite a feat crawling out at the times that you guys do. Fantastic presentation. I mean, as we speak, we've still got 23 participants and you started with 28. So I think it's been a very, very good topic. While I'm talking, if there are any questions, then please put them on the chat and Steve's happy to address them. The one thing that Steve has on the chart is basically the feedback. Again, the session is 1BD. And if you could fill in the feedback form, then hopefully Steve can come back next year. I would certainly support it anyway. If you don't know where it is, where you find it is go to the agenda at the bottom of the, once you click on the subject, at the bottom is the feedback. And the other thing is, if you click on Steve's, you'll find his contact details if you don't have trouble to get the presentation. So you can reach out to Steve. The last thing I'm going to mention is the charities that we support. Please, I know that there's been no admission charges and would encourage everybody to support the charities that G-Guide share. And even Mark Wilson commented that, you know, if you put anybody who pays over £100, he will mention them in the closing speech. While I've been talking, there's been no more questions. I think it's been a thoroughly good session, and I am going to bring it to a close. So once again, thank you, Steve, and thanks for everybody attending. Have a good day.
All right, guys, thanks a lot. Thanks for your attention, and please let me know if you have any other questions. And thanks for inviting me to participate with GSC. So take care.
Cheers.